I'd like to talk a little bit about complex zeros of a polynomial, but before we actually talk about the zeros of a polynomial, I want to do a short review of complex numbers. So complex numbers are numbers of the form a plus bi, and I is what we call the imaginary unit. And I squared is equal to -1. That's actually the definition of what I is. Or we can also say that I is equal to the square root of -1. This is probably how you've seen it in the past. So I have a few examples here that I'd like you to, if you remember this from last year, I would like you to actually stop the video, work them out, and then you can just fast forward to the answers. If you do not remember this, I'm going to go over it right now. So for number 1, we are writing our solution in standard form a plus bi. We're going to combine our real parts, which are 3 and 8. That's going to give us 11. We're going to combine our imaginary parts, which are -5 and +2. That gives us -3, and then that's going to be times I. Similar idea for number 2, except do not forget to distribute that negative sign. Sometimes people make that mistake. So for this one, we are going to get -8 minus 3i. Number 3, we're going to multiply this just like we would multiply any product of binomials using the FOIL method. However, we have one little thing that's different in the end. So we're going to do our first terms. 2 times 3 is 6. Our outside, we get -8i. Our inside, we get plus 6i. Then we do our last. We get -8i squared. There is one difference between this one and if I was just our variable. I squared, we know, is equal to -1. So we're actually going to replace that I squared with a -1. So we end up getting 6. I'm going to put -2i, I'm going to combine those middle terms, -8 times -1, which gives me 6 minus 2i plus 8. My final answer for this one is 14 minus 2i. For number 4, we're going to do the same thing, except you might notice that something interesting happens. When you multiply this out, you actually end up getting 25. And the two middle terms cancel out. This is actually a difference of squares. We get 25 minus I squared. We know I squared is the same as -1. So we end up getting 25 plus 1, which gives us 26. So this brings us to the next thing. This is a special type of multiplication problem because 5 plus I and 5 minus I are what we call complex conjugates. So a complex conjugate, here's the definition of it. The definition is, it looks a lot more confusing than it is. So if our complex number is a plus bi, we usually denote complex numbers by z. Then its conjugate, which we denote by a z with a bar over it, is equal to a minus bi. You'll notice I wrote the a plus bi with the bar over it. That means the conjugate of a plus bi. That's just a little bit of notation that you might see. You probably will most likely see that in college if you do see it again. So a few examples. We already mentioned that 5 plus I and 5 minus I are conjugates. We also, if we have something like -6 minus 2i, -6 plus 2i is a conjugate. Just make sure that you don't change the sign of the real part of it. You're only worrying about the imaginary part. Complex conjugates are really useful because if you multiply them together, you get a real number. So one of the other useful things about knowing complex conjugates involves what's called the conjugate pairs theorem. Basically what it says is that if you have a polynomial and you have a complex number that's 0 of that polynomial, then that conjugate of the complex number is also a 0. So let's do a few examples of those. For our first example, we have a polynomial function of degree 5, and it has the zeros 3, 4i, and 1 minus i. Now, one important thing to know is that if you have a degree of 5, you will also have 5 complex zeros. Now, in the past, whenever we've had zeros, they have also been x-intercepts. And so you could have looked at your graph and determined the number of zeros that you had. In this case, however, when we have complex zeros, they're not going to always cross the x-axis. So the only one actually that will is going to be this 3 because that's the only real zero. Complex zeros are a little bit different. So we have one real zero here. We're going to have 4 that are complex, which means we only have one x-intercept. I'll actually give you an example and I'll show you what the graph looks like. You don't have to draw them by hand or anything like that, but you can see kind of what these types of things look like. Just make sure that you remember that complex can include real zeros, like 3 here, and it also can include imaginary zeros, like 4i and I minus 1, which has both a real and imaginary part. Okay, so we know that one of the zeros is 3. We also know we have 4i and we have I minus 1. The other two zeros are going to be the conjugates of these two things. The conjugate of 4i is negative 4i. The conjugate of I minus 1 is I plus 1. That's actually my answer for this one. That's all I need to do. In example number 2, we are trying to find a polynomial function of degree 4 whose coefficients are real numbers that has zeros of 0, negative 1, and 2 minus I. So if you remember what I was just mentioning before, degree 4 means that we have a total of 4 complex zeros. So we already know 3 of them, and 2 of them are real. One of them is complex. The other one is going to be the conjugate of 2 minus I, which is 2 plus I. So the way that we're going to find this polynomial function is by remembering that our factors are going to be written out like this: x minus 0, x minus negative 1, which is x plus 1. With our complex numbers, we get x minus 2 minus I. We also get x minus 2 plus I. Be really careful here. I want you to notice that this thing right here will always be minus. A lot of people notice that there's like they think the conjugate, so they try to change the sign there. When we're looking at factors, however, it's always going to be x minus whatever your number is. Now, there's going to be occasionally you will have things that when you distribute them, they change signs, like that the negative and the negative here. If you distributed, they would change signs. We're not going to distribute, but I would be very, very, very careful. Make sure that you write this out like this, and then you can simplify it later on. You can distribute your negative later on, but make sure that you have a minus in your factor there. Okay, so I am going to give you a little hint, and that is do the conjugate stuff first. Otherwise, you are going to get something really, really, really complicated. So when we do these two factors multiplied together, we're going to use the FOIL method. So our first term, we have x times x, which is x squared. Then we do our outer term. So we have I'm going to color code it. We have minus 2 plus I times x. So we get minus x times 2 plus I. Then we're going to do our inner term. We get minus 2 minus I times x. So I get minus x times 2 minus I. Then our last term is negative 2 minus I and negative 2 plus I. So that gives me negative times a negative is a positive. Then I have 2 minus I times 2 plus I. So there's a lot going on in those parentheses right there. We are going to simplify it out. I do recommend not skipping any steps until you get really, really, really good at these and you feel really comfortable at them. because otherwise there's loads of places to make mistakes. So we get x squared. We're going to distribute this negative x. We get minus 2x minus ix. Distribute this negative x again. We get another minus 2x, and we get a plus ix. Then we're going to use the FOIL method again for that orange part. So that gives us 4 plus 2i minus I squared. Now we're going to simplify everything in those parentheses, and if we did everything correctly, we should have no i's in the end. If you get i's in the end, you're going to have to go back and see if you can find your mistake. So I have an x squared here. I now am going to do, okay, minus 2x, those two combine to be minus 4x, minus ix and plus ix, those cancel out. So that's a good sign. We lost an ix term. Then we have plus 4. Then we have 2i minus 2i. Those also cancel out, which is nice. And our last term, negative I squared. Remember that I squared is the same thing as negative 1, so we get minus negative 1. We end up with x times x plus 1. And when we simplify this all out, we get x squared minus 4x plus 5. The next part just does stuff that you probably did last year. So you can simplify the next part however you want. There's no way that's easier than the other. I'm going to distribute my x to my first term first. Make sure you aren't distributing the x to both parentheses, by the way. So I end up with x squared plus x, and then I have this stuff right here. So then you're just going to simplify out the next part. Be careful, there's a lot of places to make little math errors. Just go slowly. So I end up with x to the 4th. I get x squared minus 4x gives me negative 4x cubed. X squared plus times positive 5 gives me plus 5x squared. Now I'm going to multiply my x times all of the terms in the second parentheses. So I get plus x to the 3rd minus 4x squared plus 5x. The last thing that we need to do is simplify it out a little bit. This is stuff that you probably have been doing for several years, so it shouldn't be too terrible. Just don't make any little math errors. And this is my final answer right here. So you will not be expected to draw this by hand. However, I am going to show you what the graph of this looks like. It is a 4th degree function. It has a 0 at negative 1. It has a 0 at 0. It goes up and it kind of has a little squiggle in the middle of it. And so it looks like this. So you'll notice that we actually only intersect the x-axis at 2 places. That's where our real zeros are. The complex zeros kind of help determine what's happening in the other parts, the squiggle parts later on, but the x-intercepts are only going to have to do with our real zeros. So our last example is kind of a tough one. We have a function. We know that the function has a 0 of 3i. We would like to find the remaining zeros. So first of all, I want you to notice that this is a degree 4 function. So there are 4 complex zeros. We know one of them. We know one of them is 3i. And actually, we also know that the conjugate of 3i, which is negative 3i, is a 0 of this one. So what we can do now is we can find our last 2 zeros using polynomial long division. So the first thing that we're going to do is we are going to remember that we can write this out in factors. So we know one of our factors is x minus 3i. We know another factor is x plus 3i. It's minus and negative 3i. We don't know our other 2, but hopefully we can figure out the other 2 by using polynomial long division. So what I'm going to do with this, I'm just going to leave these 2 factors open. with this x minus 3i, x plus 3i, is use the FOIL method to multiply them out first. I do not want to deal with those i's. I know that if I multiply the factors that have conjugates, the i's are all going to go away, which is really nice. So if I do that, I get x squared. My outer is plus 3i, my inner is minus 3ix. And then my last is negative 9i squared. So my middle terms are going to cancel out, which is nice. My negative 9i squared ends up being a plus 9 because it ends up being negative 9 times negative 1. I still have two factors missing, but luckily I now have a nice factor. It's not perfect. Unfortunately, I cannot use synthetic division. I do have kind of a long polynomial, so I can find these two factors by dividing. So I'm going to divide f of x by that previous factor, the x squared plus 9. So I'd like you to pause the video and try this on your own. So we are going to start by doing the 3x to the fourth divided by x squared. That gives me 3x squared. I then multiply 3x squared times x squared plus 9. So I get 3x to the fourth plus 27x squared. I do want you to notice that I'm going to put the 27x squared underneath the 25x squared. Change this to subtraction. And I also have to bring down that 5x cubed. So don't forget that step there. And I am also going to bring down the 45x. Next thing, I do 5x cubed divided by x squared. That gives me plus 5x. So I get 5x cubed plus 45x. This is actually looking really nice because some things are going to cancel out. So I'm now going to change again to subtraction. And I have to also bring down my negative 2x squared. So these cancel. I bring down my negative 18. If I divide negative 2x squared by x squared, I get minus 2. And actually, if I multiply that back out, I will end up getting a remainder of 0, which is also nice. So I just change this to subtraction, meaning they actually change to adding. I have a remainder of 0. Actually, on these problems, you must have a remainder of 0 to solve them out. So if you don't get a remainder of 0, that means that you made a mistake. So I now have f of x is equal to x squared plus 9 times 3x squared plus 5x minus 2. So this right here, I know that x squared plus 9 cannot be factored. However, I'm actually not going to give you any problems where you get something else that can't be factored. The other thing will be able to be factored. You will be able to solve this out. If you are not sure how to factor it, you can use the quadratic formula. That is also fine. But when I factor this, I end up getting 3x minus 1 times x plus 2. You can use whatever factoring method works best for you. So this is the factored form of my polynomial. Make sure that you actually don't just write this as the answer. We're not looking for the factored form, we're looking for the remaining zeros. But luckily the remaining zeros are easy to find. You just set each of these factors equal to 0. I get 3x minus 1 equals 0, which gives me x equals 1/3. I get x plus 2 equals 0, which gives me x equals negative 2. So I also knew that my third zero was negative 3i, so these are my 3 zeros.